Word up. Nationwide hated. Nickel plate.
Sequel or death? Yo, son, what are you going to choose? Yo, check it. This seminar is filmed at Carnegie Mellon University. Thanks a lot, Google.
Hi guys, let's get started. We're super excited today to have Lloyd Tabb, the Lloyd Tabb. He's going to go through a long list of everything he's done in his career. It's pretty amazing. Now he's at Facebook or Meta working on the Malloy language itself. He worked on DBase for Windows back in 1992. That's old school database for anybody who knows of these things, and it's very impressive. And so again, we're super happy Lloyd spent time with us, talk about the new language he's been building to replace SQL at Facebook. Lloyd, the floor is yours. Thank you for being here.
Great. Well, thanks for having me. I'm excited what we're going to get to present today. I'm going to first take you through a little bit of the background of how we got here. Picasso used to, when he was painting a picture, he painted it over and over again. And some of his masterpieces, he painted over 140 times. I seem to be building the same thing over and over again, hopefully each time getting a little bit better. Back in the early 90s, I was building an application building environment called DBase. I wrote a native code compiler for it in '87, and eventually I wrote the first application server for the web, which was a database and a language and a web server hooked together. Later on in my career, I was CTO of a bunch of different companies, and as a CTO, my job was to make sure that everybody who was in the company could understand what was happening in the data. They were internet-based companies. The only way you can understand what's happening is you can't see your customer. You actually have to understand it through data. And the tools that I built allowed everybody to kind of do an investigation into that. After building it the third time in 2012. I realized that there was a company in that, and so I started working on a company called Looker. Me and my co-founder Ben Porterfield started building it, and by 2019 we were 1,000 people. We were in use in most of the Fortune 500. It was a semantic modeling based language, but it basically presented data interface to everybody in the organization so they could understand what was going on. So the same kinds of things that I was building earlier. Once we got acquired at Google, I started working on the next generation of those things, Malloy. Recently that team moved over to Meta, where we're doing it all in the open source. And so I'm going to show you, I'm going to talk today about Malloy. I'm going to challenge some of your ways of thinking about data today. When we work in data, we're almost always working in a rectangle. You start with Excel. It's rectangular. You can add columns that are projections. You can group by. You can do lookups. I think that one of the reasons. You've had a lot of people come in and talk about SQL, and the biggest problem that you'll see in most of these things is SQL's reusability. And the problem, I think, our thesis on that is that everything that you do in SQL operates through a rectangle. We're going to show you why that doesn't have to be. So the goal for Malloy is to enable a reusability paradigm the same way that you would have for a function library. In order to use Twilio's API, you don't have to understand how Twilio works. But when you're working with data, you get a pile of tables and you get a bunch of instructions about how they're related, and you have to work that out for yourself. There really is no API. Even if we change the syntax and make it a little easier to use, we're still always reconstructing that logical relationship every time. And we think that there's a way of building an abstraction around those relationships and then reusing that. Sorry, there was a slide that I missed. Okay, so what are the operations within a rectangle? Inside of a rectangle, it's filtering, grouping, projecting, windowing. These are the basic operations that we use after the join has occurred. In SQL, this is the slide I was looking for. We first take a bunch of rectangles, we join them together, and then we perform, and then we get a new result. And those operations occur at this last phase. And I'm going to show you why this is a problem. So let's start with a really simple use case, which let's take orders and items. And these are two tables that we're interested in doing some queries against, and they're really simple. right? I want to calculate two things. I want to calculate the total shipping cost in the orders, and I want to calculate the total revenue from the items table. When I ship something, there's only one shipping cost, and so I can sum the orders table and get the total shipping. Pretty straightforward. When I want revenue, I basically can go compute that from the items table. Now let's take a look at it by order date. Okay, so I can group by order date, pretty straightforward, and I can compute the shipping. Or I could compute the revenue from the same query, from the same relationships, right? But how does revenue relate to shipping? I want to look at it, I want a table that looks like this: order date, revenue, and shipping. How do I get that? Well, you would think you should be able to write it this way. I have my join relationships. I have my new rectangle. I sum the items and I sum the orders, but this result is wrong. Why is the result wrong? So this is when I was interviewing at Looker. This was the interview question that I would throw up and see if anybody could answer why this was wrong. And it's because when you do a join, the data fans out. Right. So when I join these two things together, the orders are repeated for each item row in the item. So because there were two items from with the order one, it gets repeated, and for the second one it gets repeated, and then for the third one it gets repeated. So this all makes sense, right? This is the way we work is that we combine rectangles when we're doing traditional data warehousing. So how does this work? So if I wanted to do this computation, first I produce a rectangle with the dimensionality of order date for shipping. Then I do the same thing for revenue, and then I join those two things together. And so it looks like this: I produce two rectangles, and then I produce a third rectangle that I've joined. If I want to change that to another dimension, like user, I have to repeat myself. I start with the order date query, and I have to modify it in all these places in order to get a query that works on user to look at it by a different number of dimensions. So what this does is it multiplies the number of tables that we have. So we have a lot of artifact tables lying around. You can either materialize any of these or write them as CTEs, or you have a lot of duplicate code that's almost the same in a lot of places. So this is the nature of the traditional data warehousing problem, and the question is, can we solve it? And so enter Malloy. Malloy makes the promise that join relations don't affect aggregate calculations. When you declare a join, you declare it in the net. When you declare a join, you declare it in the network in something called a source, which is a reusable object. When you're making references to these calculations, they're guaranteed to be correct when you get the results. Okay, let's take a look at. So this is a source declaration.
Wait, sorry, can you go back to the last slide? That went by fast. Sure. Sorry. In query operation, aggregate calculations are applied. The aggregate calculations can reference any locality in the joint network and will compute results correctly. Okay. I mean,
we're gonna. I'm going to take you through it.
Okay. Thanks.
Great. Okay. So this is a source declaration. It's not a query. It's a source, and it's describing the relationship and the aggregate calculations. And we'll notice that this aggregate calculation is written slightly different. It's written navigating to the place in the network where I want the sum to occur. So we're starting with an orders table. We've joined items. We do items.price. We're navigating to the number we want to sum, and we sum that. And that'll give us total revenue. And the shipping cost is in the top level thing. And so we navigate to just basically the top level thing. We do the sum. And now I don't have to work. My queries become really easy. So this produces something that looks like this. This is the API to this data. I can pick from any dimension or any measure and get correct results. I can group by it. So I can pick from anything in this thing in a query, and it guarantees to produce correct results. So it makes queries really simple. So this is what a Malloy queries looks like. We group by order date, and we aggregate total revenue and total shipping, and it produces the right result. We run order items, and we group by user ID, and it produces the correct result. We want just the total revenue. It produces the correct result. So there's the query on the left, which is SQL or any SQL-like dialect, and then the query on the right is Malloy. This is how it does it. So what we do is we collect the ability to distinct the rectangle, either by creating a key or using the primary key, aggregate, basically distinct those values, and then sum those values. So there are several different ways of doing this. There's other ways of using with sum distinct. It's really dialect dependent, but this mechanism is something I've written about. It's called symmetric aggregates, and it guarantees that aggregation is computed to a particular rectangle in the join. Okay. So this reusable API to data guarantees that we get correct results and we get a really simplified interface to the data. It also means that we have full dimensional freedom within a network. So you can imagine that you've joined a whole bunch of things together and maybe even done some even joined some queries together. And then from within that network, you can just, your queries are really simple. Okay, so that's the first innovation. The second innovation is nesting. It turns out that data is not rectangular. It often comes into us as a network. So this is a JSON table of the same data. We had two tables, but it could be one table, right? And it's basically we have, for each order ID, we have an array of records that's nested. So in this case, we're just seeing what it looks like, and this is what the schema might look like in DuckDB. And when you make a source with nested data, we automatically join it and know how to unnest it. And so the interface to this source is exactly the same as the interface to the data in the joined case. Okay, so we looked at it before where we joined orders and items and it produced this interface to data. Whether or not the data is nested or joined is irrelevant to Malloy. I mean, to Malloy user. We just know that we have a reference to items, and I can still do the same calculations that I want. So I can write a calculation against this that looks exactly the same. Is that making sense so far? The other side of this is arrays and structs. So Malloy Looker worked on 30 different dialects of SQL, so I got to know them very well. Malloy works on about, I think, 8 now. Everybody does array ag and structs very differently and unnesting differently. What Malloy does is it's something really interesting. It turns out that an array ag is really just a nest of a query. And so Malloy allows you to, anything that you can do in a main query, like grouping, having, filters, it also lets you write it. So in the simple case, in this case, we're building an array of items by order date. But we can do something even more complicated. We can do it with aggregates in the middle of them too. So we have our order date and we can nest the items. And for each row, we produce a record that has the aggregate calculations and the thing. And so there's a recursion that occurs here that's really interesting. It makes building hierarchies of data that you can then use in pipelines really easy too. So I'm going to demonstrate this. So it'll be more interesting when you see it. And again, this is what the query looks like when you start writing this kind of thing. There are other innovations that are in Malloy that some of them I'll get to today and some of them I won't. There's ungrouped aggregates, which means we have an all function which escapes grouping, which is really useful for computing percent of total or percentages. So a lot of times when you're writing a query, you kind of want to know what this thing is related to the other things that are in the query. That's native to Malloy. Annotations and rendering allow us to tag any element in a query so that it can be so that something using the data downstream can take metadata and apply it, and that's built into the language. Dimensional indexes are ways of knowing the low cardinality dimensional values to a network of data. So you can have AI be able to respond, and for LLMs, it's really great to feed LLMs those values. And Malloy has composite sources, which basically allow you to do multiple inheritance of sources to create to access cube data for really large data sets. And we do that. We're using that at Meta.
Wait, can you explain the dimensional indexes again? Do you just mean something like where you can like jump to the offset in a multidimensional array?
No, so I have a network of data that I've joined, orders. The interesting dimensional values might be the user's name, the product name, the category, the state of the user, right? I want to know what the low cardinality values in that data set. So when a user says, show me orders from New York, it could know that New York is probably the user's state. So it can map the dimensional value of New York back to a field properly and know how to filter it.
Got it. Okay. Yep.
Okay. These are the databases we currently support. And we're going to go into a demo because that'll be much more interesting. So let me stop sharing. Okay, this is Malloy. The first thing, I'm running VS Code, and in VS Code, I'm installing the Malloy extension. And the Malloy extension has DuckDB built into it, so it can read and write Parquet files and CSV files and JSON files. It also lets you connect to other databases, like all the other databases that we support. So it's your development environment for Malloy. This is an orders.json file that I created to match what we just looked at. And here is the orders.malloy. So this is the code we were just looking at. So the schema for this is it has items, and these are the items that are in it, right? And I can so above you'll see that there are these things that are called code lenses in VS Code, and when you click on them, they run something. So I can preview this data, and we can see this is what the data looks like previewed. We can here are some queries, the queries that I was running, so we can run that. We can also see the SQL for the queries that we're running, and we can see it in JSON and HTML. And so here are the actually. And so we can do that too. Now, additionally, there is an Explorer, which gives us a visual query builder for this data. So once I've built a source, I can actually run queries against this by using the visual query builder. We can say group by items.item name, and we can aggregate total shipping, total revenue, and run that. And I can run a query, and it will write the query for me. I can go over here and I can add things like order count or item count. And reload that. And then I can go add more aggregates. Aggregate. And run that. So the development environment lets you build this, and then what happens is I can go over here to this Malloy tab, and I can copy this query out, and I can go back and put it in my model, and I can run it. Okay, so there's a development flow for building your queries, running your queries. Everything that you do in the Explorer turns into Malloy and SQL, and so this is the basis of your development environment. And now let's go build some models. Okay, I have a airports query. I have an airports table that's basically a Parquet file, and it has a bunch of columns in it, like city and state and code for the airport and various things. And I've added some measures to it. Airport count, average elevation. Notice that I'm running at elevation.average. And this is a tag that tells me that I want to display it like a number. So this is basically whenever I get whenever I get a query, whenever this thing shows up in a result, it's going to use this to render. And whenever percent of airports shows up, it's going to show it as a percentage. The all calculation is a ungroup expression that will show me 100%. Will show me all of the values that are escaping grouping. So let's go explore this. We can group by. Let's group by fact type. Where is that fact type? And then let's aggregate airport count, average elevation, and percent of airports. So 73% of the airport, 70% of the things are airports, 25% are heliports, and these where they are, right? I can one of the things I can do here is, so let's take this Malloy, and I'm going to, instead of writing it as a source, I'm going to write it as a query. Now, we haven't seen this yet, but you've seen the case where I have the run statement, but I can also declare views inside a source. And you can think of this as a member function in object-oriented programming. It's basically this query, and it assumes that it's running within airports. So if I run this now, this is going to run here, and I can build another one here. We saw state was here. And I'm going to do by state. Does the member function thing make sense? So where about this? State. Okay, and now I can look at the airports by state. Oh. The difference between, I could run this query, or I can place it within airports, and it is a view within airports. So what happens now is when I explore, I can load by fact type and run that. And I can, or actually, let's do it the other way. Let's load it by state and run by fact type. So now for each state, I'm getting the number of different facilities for each state. Is this making sense? So the idea here is you build reusable components in your source, the common ways that you're going to use the data, and you can mix and match and combine them. So this is showing me for any given state what are the breakdown of the heliports. I can also flip this around. I'm going to do something else. I can tag this. This is annotation. I'm going to make this a shape map. And now when I run this, it's going to show me as a shape. The only difference here is that in the metadata, I've marked that the state is a shape map. There's an annotation here that says that this is a shape map. The thing that takes the results and displays it recognizes that by state should be rendered as a state map. And so when it sees that, it knows how to render it that way.
Is the views are they being materialized, or are they only accessed like when you actually query against them?
So they're basically they basically help you. They're a way of writing code against airports, right? So for every one of these, I can either run them, show SQL, or I can explore them. So each of these these are just basically common queries for airports. You can think of them as common queries that I would want to run against airports, and then you can mix and match them. But the really interesting thing is because of the nesting architecture, you could combine them. So when I explore, let's look at it by.
It's lazy materialization. It's not like DBT where like if you declare a bunch of these views, it's going to make them all for you. This is like
no, it doesn't. There's no materialization. Every single Malloy query runs as one SQL query.
Got it. Okay, makes sense.
So like when I run this is the Malloy for this, right? this will convert to one SQL query. And when I add nest by state, and I look at the SQL, it changes the query, changes this query, and when I run it, it's basically showing me the seaplane bases are on the coast, obviously, right? And heliports are in Texas, and so
scroll down. Go back. Where's the balloon ports?
Balloon ports?
Yeah, that was the last category.
Yeah, okay. Let's.
Sorry.
Actually, so we can write this query really. See, the other way to write this query is run view. Okay, so this takes the fact type query and then appends a nest to it. And so now when I run that, I get there's your balloon ports.
Illinois. Okay. And Delaware. All right. Yeah. So
Okay.
Someone had a question in the chat. Says, are many-to-many joins allowed in the source declaration, or do they have to be many-to-one? If the former, are the semantics defined, so the duplicates are removed by default?
Duplicates are removed by default. But let me show you. We're about to get into joins, which is okay. So this is airports. Really simple. Great. Now let's take a look at flights. Flights imports airports. Right. This thing that I just wrote. If I look at the schema for it, all the stuff that I just did was here. I can run combo, and we have but I've imported it like you would in a module in any other language, right? And the interface to that is very clear, right? And in flights, I'm joining an explicit table carriers, right? But I'm also joining the airports thing that I imported twice, once as origin and once as destination. And then I'm adding some measures, flight count, percent of flights, and percent delayed flights. So pretty straightforward, pretty simple. I can now go explore flights, right? And I can build queries that are based on airports. So if I want to group by, let's go look at the origin state. And I'm going to aggregate, we'll do flight count, percent of flights, the percent delayed, and the number of destinations. Oh, hang on, results. I'm able to use this network just the same as if once it's built, I've got this interface to data that I can do, and I can start saving these views. So if I want to go grab the Malloy for this is what this looks like. We'll grab this as a source. We'll do by state. Right, and now when I run this, I get, and we can go explore this, and let's change this to carrier. Let's add a group by, let's see, we'll get the carrier's nickname. We'll run that. So we could save this, or we could nest by state. Oh, oops, I did it wrong. Hang on. Group by carriers.nickname. And then I'm going to nest by state. And I'm going to take this and let's limit it to the top 10 states that each of the carriers flies. And we can run that.
Is the measure keyword basically like a projection? Or do you define what the output is?
The measure keyword is defining an aggregate. So measures are defined as aggregates. Dimensions are scalar calculations that are written against the source. So the measures are within the source. You basically you've got some data, you want to aggregate it. It's a measure. So it's a count, a sum, a max, a min, an average, standard deviation, those things. So it's about a set of data, and it's tied to and then I'm not showing this here, but dimensions are scalar calculations. So like if I wanted to combine the city and state or something into a field, I can do a concat. That would be a dimension. And those then just show up like regular columns.
And presumably you have like regular expressions for matching and all the data clean crap people want.
Yep.
Got it. Okay.
All right. So like let's take a look. So this is a more built out flights. So it's something that it's just a demo of that. So it has this is a bigger version of that. So it's got the carriers, it's got the airports, it's got aircraft models, it's got aircraft, and so this version of flights is more built out, and I can go look at the top carriers and I can run that, right? And let's do that. And so, or I could look at it by manufacturer, and we can look at that. And okay, well, we can then see which carriers. Then we can look at the manufacturers by carrier if we wanted to. So we could nest top carriers here and run that. And so we can see Boeing sells to Southwest mostly, and Airbus is used by United, right? And so you have the ability to really work with the data very quickly once you have this model built is really the power of it. It's the design here is build a reusable object that you can then that you can then make easy queries from. Okay, this is so there's an index operator. It's like group by, except it produces a table with 4 columns in it. So I'm going to run this. So let's take a look at this. So origin with DAL appears on 1,600 rows. Phoenix appears on 12,000 rows. PHX. Cleveland appears on 5,000 rows. Atlanta appears on 17,000 rows. So once you build this dimensional index, there's a lot you can do with it. One of the things that we do is for filtering. So if you go and you want to filter this data on San Francisco, you just type San Francisco. We can filter on San Francisco International Airport, right? And so once you have a dimensional index, you can reason about the data much more easily. So this is what the index basically says, which of the dimensional columns am I interested in indexing? And then they're available. And it's a pretty interesting SQL query that it writes to produce this dimensional index. Any questions? So questions so far?
For that dimensional index. Sorry, go ahead.
Yeah, I wanted to go back to the question of many-to-many joins. I was wondering, were you still trying to cover that, or?
Oh, sure. Okay, so in the joins, these are join ones. Right. There's also a join many. So in this case, there is one carrier. When I join from this relationship, there's one carrier on it will join to one row in the resulting table. In a nested case, it's a join many because one row will have many rows. If I flipped it around, if I had a carrier and I was joining in flights, that would be a join many, and a many to many is a join many. And so when you write your aggregate calculations, you specify the rectangle that you're going to write it against, and it will produce the correct results for both rectangles.
Okay, maybe I need to look at some of the examples on your webpage better, because if it's a many-to-many and you're doing a aggregate on one of the attributes from or measures from below in the chain, feels like there will be an intricate issue with duplicates, like sort of duplicate counting of something that I don't understand how you get around.
Yeah, let's.
It's okay. We don't have to do it.
Because you navigate to. So if we look at, let's take a look at orders again, and let's take a look at this query. So because orders, so this is how we dedupe. It knows the distinct key of the rectangle. It collects the distinct values, right? And then it unnests them and sums them. And so that way, so there's two forms of sum. One is a distinct sum and one is a regular sum. And because of the way that you declare it in the language, we know whether to write a distincting sum or a normal sum. And in a many-to-many case, we're always writing a distincting sum.
Right. Okay. Thanks.
You bet. Other questions? Okay.
Wait, actually, one more in the chat. Once a model is ready, actually, hold up, Keisha, let me read this one. I'll go back to you. Once a model is ready, how are Malloy queries productionized? Leverage the resulting queries, views, say in Power BI or Tableau, or any visualization dashboarding platforms.
Got it. So we're building a core technology. There are four or more companies right now that are building on the basis, are building products that are on the basis of. There's something called a Malloy Publisher, which one of the companies is using an open sourcing, which will take the output of our notebooks and publish them. The Tableau and Power BI don't have any notion of this of aggregating the way that we do, so we don't integrate very well with them. But we envision that there will be more open source alternatives to use Malloy. We're at Meta, so we're building something internally at Meta that lets people explore the data. This exploration tool is also available as a separate installable component. So the Explorer that you're seeing here is also a component that's available on our website. So we're building pieces. We haven't built the whole thing yet.
Yeah, sure.
Long way of saying it's in VS Code right now, and you can build your own application.
Prakash, go for it.
So I might not have fully followed it, but you talked about modularity. So what you're saying is that like the views in SQL do not provide the level of modularity that you're looking for, or
Yes.
there is people have been doing, like they've been sharing SQL snippets through views, etc. Right? They've been doing what you just showed, right? So
let's go back to let me go back to the deck for a second, then I'll explain.
Yeah, that thank you.
Okay, so in this case, each of those CTEs could be a view, right?
Mm-hmm.
But what they are is they're forced at a granularity of user ID, right? So a view is really just a table. It's not like whether or not it's materialized or not, whether or not it's if it's a query, if in this case it's either a table that is materialized at some level of granularity, and what the difference between our source and a view is, the source is independent of the granularity. You have total dimensional freedom to pick any dimension or any measure, and you can get a correct result. A SQL view is fixed at a particular granularity, and so you end up with lots and lots of them. You will end up with when you talk to somebody who's working with SQL, they'll tell you they have 10,000 tables in their data warehouse. What are the 10,000 tables? They're really just copies of the data at an aggregation level and a granularity, and that's why they have some, right. And it's because you have to produce these rectangles in order to be able to do your analysis. And so whether or not it's materialized, whether or not it's a CTE, which you have to copy, a view, which is again it's a copy of the code in the database, or it's a table, it's all the same thing. You just end up with lots and lots of copies of these things. Whereas a source, it's a recipe on how to write the query, not the query. Now our views are also at some level of granularity, right? And we use that building block differently for the nesting, and so we can produce views in Malloy, but the real power is the source.
Mm-hmm. And I'm just curious that could you have extended SQL to produce those flexible views at different levels of granularity?
Which SQL?
I don't know. I'm just asking that question. Like, could you have, instead of like creating something totally new, could you have extended?
You're basically looking at the fourth rev of Malloy. The first attempt was to make it very SQL-like. The problem is SQL's clauses are order dependent. They're the number of how do you declare something like a source and its joins? There was just different enough that we couldn't get anybody to understand it. So we built it that way. We showed it to people. They didn't understand it. Malloy is a little more complex than a single query, but also but in the end simpler.
And so the one last question. So if you work with ORM tools, like they generate SQL, which is usually not very efficient, like it's like a boilerplate. Do you think Malloy might run into those similar issues and it's very hard to kind of after the fact, like dig into SQL and figure out what the inefficiencies are and how we could have written it better?
Actually, we find that we're in many cases we're much better. If it depends on what you're trying to do. If you're trying to do something dead simple, we're dead simple too. Like if you're doing simple queries, you can get yourself into trouble by writing really complex Malloy queries. There's no question about it. But you couldn't possibly write them in SQL. So in the general case, most people use SQL relatively simply. They pull a data set and they feed it into something like Pandas, right? And what we're trying to say is you can do more with these database engines are really powerful. We leverage the power of these database engines in a way that's pretty unusual. And so we find that people can abuse it, but generally we're not bad, and we pay attention to performance.
Okay. Yep.
So that was my presentation.
I will clap on behalf of everyone. We still have 15 minutes or so for questions. If the audience wants to fire away.
Sure, I'm happy to answer any questions. I'm going to stop sharing.
Mo, do you want to go for it? Actually, you can keep the share screen.
Okay.
Because I'll
So I was, that's really interesting. Thanks for the presentation. And I guess I was trying to connect it to things like the nested relational algebra and stuff like that. And one question, a more specific question I have is, there do exist some languages, maybe not really widely adopted, that sort of allow you to do some of this through dot notation. You can do joins through dot notation, and in some cases you could do aggregates after doing that. Right? Did you explore whether this would be similar to semantically to that?
So yeah, so the difference between many of the other dialects that you have seen is that they don't have a notion of a source, right? They're simply doing what SQL does in a pipeline state, right? But they're not building reusable aggregation that are guaranteed correct, right? And so you end up having to re-express the aggregate calculation over and over again.
Right.
In a Malloy model, the calculation for revenue exists in exactly one place, not 15 files, not in 15 queries, in exactly one place, right? And it's guaranteed to be computed correctly no matter how you join, no matter how you dimensionalize this data. That is the core difference, right? And I don't see the other. Yes, you can make. We can argue that a dot notation is more readable and we do have dot notations where you traverse to the object you're going to sum and do that. But the core difference here is building an abstraction that is easy to understand from the outside.
All right, thanks.
Did you want to go for it?
Sure. So according to my understanding, with an explicit materialized view, there's opportunities for optimization with incrementally updating it. I'm just wondering, in the context of this system, what kind of opportunities would exist?
Yeah, so not showing it here, but any one of these queries could be materialized, right? So one of the things we were working on is an annotation for materialization, so that if we didn't get into it, but you can have sources that are based on queries. Those sources can be materialized, right? And so it's just because Malloy always writes SQL and it always writes everything as a single SQL query. The materialization of that is just the same as it is in SQL. And in fact, we have something. If you go read our docs, we have this thing called the turducken, which is inside of a SQL statement. You can reference a Malloy query, and inside of a Malloy query, you can have it based on a SQL source. So we interoperate with SQL in the same way that C and C++ interoperate or JavaScript, and we treat SQL like assembly language, but there is inline assembly language. There is inline SQL for Malloy.
Thank you.
Other questions? So my question would be, can everything you want to express now in Malloy, I understand like Looker supported 30 SQL dialects, Malloy is down to 8. Can everything you want to express in Malloy be mapped to pure SQL with built-in functions, or do you have to fall back or rely on UDFs?
All right, so you just have to be clever. So like the nesting stuff in MySQL was like a real brain teaser. It doesn't have the Malloy language has arrays, but MySQL doesn't.
Yeah.
But Malloy speaks MySQL, and it uses JSON, and basically abuses JSON so that it can implement the core functions of Malloy. The answer is most SQL dialects today you can implement reasonably well in Malloy. The SQL on each of these dialects is radically different. I mean, the way you unnest on every single dialect is different. The way that you do lateral joins is different. MySQL, Postgres support correlated subqueries. Snowflake does not, right? So how do you without correlated subqueries against arrays? How do you do the symmetric aggregate thing? Well, we use some distinct in order to do that, and so but from your point of view of using Malloy, you don't actually have to think about it.
Got it. So I think basically what you're saying is there's no user-defined functions at all.
There are. We originally were trying to say no user functions. We then have a way of escaping to use the native SQL functions with an exclamation point on a function. You can actually call any native SQL function. And recently we've decided that if you're working on people are generally tied to a machine, so we do at least in Presto, we've implemented most of the functions that you can get to in Presto from Malloy. But there is a core set of functions that are the same in all dialects.
Got it. Okay. So I didn't mean necessarily like can a user writing Malloy add user-defined functions? It was more like for you guys to translate from Malloy into SQL, did you have to fall back on using UDFs because
never?
Got it.
No, all native.
Yeah, love it. So it works. What's the biggest challenge, or what's the next big chapter in the Malloy story? Is it just expanding to more SQL, SQL platforms? Is it just going within Meta and getting more people to start using it and banging on it and breaking it and learning more from that? Or is there some big feature like, oh my gosh, we had this be game changing for us? All the above.
It's basically user adoption, right? The thing that we in public we don't have a tool that you could install and use it for your corporate data, right? And the reason we don't have that is there's a whole bunch to getting that right. There's security and access controls and a whole bunch of stuff that we haven't written, right? And basically what we do is we create an explorable interface to data. So there's a company who just got funded that is building on Malloy, and they're doing their stuff in open source. I'm very excited about them, Pathways. And then inside Meta, we're building up that user base, which is really interesting. And so as we build tooling, we're open sourcing all of that tooling to make it better. So we're actually currently re-engineering the Explorer. The permissions model, we're following an object-oriented permissions model, which is that some columns are going to be public, some are private, some are protected. So when you inherit sources, there is source inheritance. So you can start with the source and extend it, and it's an inheritance model. Anything protected you could see, anything private you wouldn't be able to see, anything public would be published. And then how does that fit into role-based access control? We're solving all of those problems at Meta, and as we do, we're open sourcing all of that.
Got it. Awesome. All right. Any last questions from the audience?
I had one more question. So
Go for it.
Looker has an intermediate modeling language. I don't know much about it, but I think Looker, Tableau, most of these systems have. So is Malloy comparable to these languages, or is it lower
Well,
level?
given that I designed the one in Looker,
Yes.
yes, it's 10 years of working on that. I learned a lot, and so there were a bunch of features. So yeah, so yes, it's comparable. It's more rigorous. It's a stronger, more complete language than LookML, which is what we built before.
Mhm.
And much of the team built LookML with me. So there are people on my team that I've been working with for 30 plus years. So
Great. Thank you.
yeah, I do want to shout out to the Malloy team. We have an amazing group. This is something not as well understood, but software is a team sport. Carlin Eng is on the call. He's our product manager. The Malloy team is made up of some really amazing folks. This is not a one. This is a many person effort with a lot of passion. So I really the team is amazing.